Let's try to solve some problems. And as I told you last time, we will be looking at that problem which you have not solved. So if you don't have that problem, you can take it down. Once again, in a gas liquid contactor, a pure gas is absorbed in a solvent, and the penetration theory: in a gas liquid contactor, a pure gas is absorbed in a solvent, and the penetration theory provides a reasonable model by which to describe the transfer mechanism. As fresh solvent is exposed to the gas, the transfer rate is initially limited by the rate at which the gas molecules can reach the surface. If at 20 degrees centigrade and a pressure of 1 atmosphere, 1 bar, the maximum possible rate of transfer of gas is 50 meter cube per meter square per second. If at 20 degrees centigrade and a pressure of 1 bar, the maximum possible rate of transfer of gas is 50 meter cube per meter square per second. Express this as an equivalent resistance. When the gas solubility is 0.04, kmol per meter cube, 0.04 kmol per meter cube. If the diffusivity in the liquid phase is 1.8 into 10 raised to power minus 9, 1.8 into 10 raised to minus 9 meter square per second, at what time after the initial exposure will the resistance attributable to excess of gas, excess of gas, be equal to about 10% of the total resistance to transfer. About 10% of the total resistance to transfer. I'll quickly read the problem once again, have another sweep at understanding it, and then we'll discuss. A pure gas is absorbed in a solvent, and the penetration theory provides a reasonable model by which to describe the transfer mechanism. As fresh solvent is exposed to the gas, the transfer rate is initially limited by the rate at which the gas molecules can reach the surface. If at 20 degrees centigrade and a pressure of 1 bar, the maximum possible rate of transfer of gas is 50 meter cube per meter square per second. Express this as an equivalent resistance when the gas solubility is 0.04 kmol per meter cube. If the diffusivity in the liquid phase is 1.8 into 10 raised to minus 9 meter square per second, at what time after the initial exposure will the resistance attributable to excess of gas be equal to about 10% of the total resistance to transfer? Okay. So I hope the English part of this statement or problem is clear to all of you. I had explained this, I'll again explain to you. Please remember, when you read this problem carefully, first mention noteworthy is the pair of words pure gas. Okay. Second point is fresh solvent. Okay. I am trying to get some keywords, so have you focus on it. Pure gas and fresh solvent. Pure gas means there is only this solute in gas phase, nothing else. We even neglect any vapor pressure of the liquid. So, even the solvent molecules we ignore in the gas phase. Now, is that clear? Whether it is possible in practice or not is immaterial. We have to go by the problem as it is, right? And when we talk of a fresh solvent, that means there is no dissolved solute gas in it. It's only solvent. So, gas phase is one kind of molecule, say A, and liquid is the other kind of molecules, the solvent, let us say B. Okay. Since nothing is said, there is no reaction. Okay. Then you can focus on these words. The transfer rate is initially limited by the rate at which gas molecules can reach the surface. Okay. It means the initial rate is governed by how many gas molecules can reach the liquid surface. It is a pure gas. Even though there are only gas A molecules alone, if any molecule has to come from bulk to the surface, it will have to face this collisional barrier, because there are other molecules of that kind which will scatter it away from its direction. So, this is a situation where the resistance is one of self diffusion. There is no other kind of molecules, only the resistance offered by molecules of the same kind, A type, only are present. But it means if you were to simply calculate the velocity of a single molecule at that temperature, that will not be able to give you the rate of diffusion actually observed or stated to be observed, because on the path towards the surface it will undergo these multiple collisions. Okay. So, the self collisional barrier, so to say, has already been put in force. Suppose a molecule can, with the distributed velocity, if it could have, let us say, a few molecules can have in almost infinite velocity, very large velocity. On the average, that will not be able to manifest in the rate of transfer. And look at this situation. You think in terms of concentration profile. Think in terms of concentration profile. In the gas phase, pure gas. So, the partial pressure of A is also total pressure. Divided by RT, you get the gas phase concentration. And that gas phase concentration will be uniform right up to the liquid surface. Right? It is pure gas. So, you would see there is no observable concentration gradient in the gas phase. Now, is that clear? There is no gradient of concentration of solute gas in gas phase at time 0. What about the concentration profile in the liquid at time 0? See, the object of my idea of education is that I train your first reactions to be right. Okay. So, do not worry if you are mistaken, but if you do not try, that is something not acceptable. So, wrong answers are okay. So, I just heard one answer, the concentration gradient or concentration profile in the liquid is also flat, concentration gradient is 0. Now, we may have to redefine diminishing as a term. Diminishing will necessitate it decreases, right? So, you are in opposite sides. One says the concentration does not change, another says concentration diminishes, and linear. Okay. The one aspect which links both the answers together is the linear part of it. His concentration profile is linear, you say the concentration decreases linearly, that is something which is common. Yet you are at the opposite sides literally, and yet both of you are in a sense, if not completely wrong, fair bit wrong. Okay. Let us take a closer look inside the. So, we had two on one side, one on the other, and vast majority nowhere. Think, try, answer. Let us take a closer look, draw the diagram, And please remember, I had explained this on the board in the traditional fashion, chalkboard method, if you remember. I didn't write too much, at least this much you should remember. The third answer which has come is that there is a step jump in concentration. Agreed. So a step doesn't preclude finite values. So let's say gas phase has uniform concentration, say CAG, whatever. In the liquid, the closer look, you take a highly magnifying lens and look at the liquid. You would see that actually we are talking of or capable of talking of two regions. One at the interface itself, and let's say that is Z equal to 0, because so far we have been maintaining that interface has no thickness, it's a plane. So that is one plane, that is the interface, and then rest of the liquid. So when it's a fresh liquid, pure liquid, and let's say we split, look at time also closer, we could say time we define in three notations. Time is 0 minus, that is before that real initial moment 0, t equal to 0, t equal to 0 minus, and 0 plus. So infinite simile on either side of this moment which is t equal to 0. So now let's see, at time 0 minus, if we permit this ideality of approximations whatever we have, then we are talking of the planar interface not being given time to communicate with the gas phase. So at 0 minus time, the concentration will be 0 everywhere in the bulk, including at the interface. So you are right, but at 0 minus time, time less than 0. At time 0, because the planar interface has no capacity, I had said that it will get immediately saturated. So whatever is the partial pressure or total pressure in this case for pure gas, corresponding to that, according to Henry's law, whatever is equilibrium concentration, that will be now at time 0 at Z equal to 0. 0. Okay. Go systematically. 0 minus we eliminated. 0 minus everywhere it is 0, including at interface. At 0, time 0, everywhere in the bulk of liquid, to the right of the interface in your mental diagram, if left is gas, interface is here, to your right is liquid, everywhere for Z greater than 0, concentration is 0, but at Z equal to 0, at T equal to 0, the concentration is Ca0 star or Ca star, gas phase concentration, in dissolved form in liquid, which is saturation concentration. Okay, so at time 0 you see only interface has the saturation concentration, everywhere inside concentration is 0, which means there is a sudden jump in concentration from Ca star to 0 if the solvent is fresh. Okay. Now if in no thickness or in delta Z tending to 0, the concentration is dropping from Ca star to 0, that means in the liquid phase the initial gradient is infinity. Okay, that's the meaning of this finite jump, Ca star to 0. Okay, so again this is the horizontal line of the line, this vertical line is also line, but this is not a gradual variation, it's a sudden variation. Okay, now look at a situation time greater than 0, say 0 plus, slightly larger than 0. You are given some finite time, an infinite gradient, so interface will be the source, it will supply these diffusing A molecules and the concentration will still drop very rapidly, but not at infinite gradient at 0 plus, because at time 0 plus you are given time for diffusion. Theoretically liquid phase diffusion can be having infinite gradient, so infinite flux. If 0 plus time is very short, under the influence of this very large gradient or flux, concentration profile will develop slightly into the liquid. It is not going to drop as a step at 0 plus. The solute A molecules may penetrate the liquid, may be a fraction of a micron, but some finite distance will be covered by diffusing molecule. So now the gradient is no longer infinity. Infinity was at 0. At 0 plus the gradient has suddenly dropped to finite value, but it's very sharp. The concentration profile is very sharp. So if I have gas here, liquid here, A here, say solvent B here, no reaction, the gas phase concentration is uniform, say CAG, it's pure gas. At time 0, this is the situation, and the concentration in liquid will be 0. So here C A will be equal to 0 in the liquid. The gradient is infinite. This darkened line is the step, finite step, representing infinite gradient, infinite flux. This is going to be picture at t equal to 0. At t 0 equal to 0 plus, I will have the gradient still sharp, very sharp, but not infinite, finite. So what has happened? Initially, the concentration profile meant at t equal to 0, the concentration is 0 here at interface also. And then at very short time t equal to 0, it shoots up to the saturation. You have rightly pointed out, I had explained this. This is only, I am focusing on the qualitative part. Actually speaking, this should be at a lot larger level, because the gas phase concentration is, because gas is rare, will be very small compared to liquid phase concentration. Okay, so this is small, this is 0. Okay, saturation concentration will be somewhere way above here. Okay, so this is, say, Cs star. All right, point is that the gradient is infinite, and therefore the flux is also infinite time t equal to 0, but at 0 plus the gradient drops to a finite value. So this gradient here in this region is very large still, but not infinite. Get that? And in that time 0 plus, this distance penetrated by A in liquid phase will be very close to the interface, short distance. Is that clear? So the question now we have to address is, at time 0, when the liquid phase permits infinite flux, can we have infinite flux in practice? Look at the problem. What is the flux given as? According to what I argued, at time 0 the gradient is infinite. According to Fick's law, we can have infinite flux. In practice, can you have infinite flux? That's number one. And second, what is given in the problem? Read the problem, understand the problem. Is infinite flux possible? Infinite chats are possible. So what is the flux given? There is a value given, 50 meter cube per meter square per second. A value is given to you, 50 meter cube per meter square per second. Now let me ask another question. Why have they given a certain finite value? When the liquid phase has the capacity to produce infinite flux. Liquid has the capacity to conduct or let diffuse infinite number of moles per area per time of A. Why is it that we are given 50 meter cube per meter square per second, a finite value? Think, understand, why are we having finite flux? You were telling me something. Self-diffusional collisional barrier. If I can supply to the interface infinite moles of A per area per time, liquid can transfer, even if for a very short time. But I just can't have that supply because molecules of A are getting reflected, scattered by its own kind. In addition, at any finite temperature, I can't have infinite velocity. So all of that will be accommodated in the resistance attributable to the gas at time 0 when liquid has no resistance. Infinite gradient, infinite flux means no resistance in the liquid. So even at that time when liquid has no resistance, gas must be having some finite resistance, and that is because of the collisional barrier and the finite molecular velocities. All of that will be reflected into certain initial resistance, which you may say is capital R subscript G. Okay. And now look at times greater than 0. I indicated here a short enough time, almost equal to 0 plus, and I can continue looking at larger times when the concentration profile will be seen to be running deeper and deeper into the liquid. So the profile will look over time as advancing into the liquid. This is how with time the profile will get shallower but deeper. Okay. And then the gradient, which was infinite in the beginning but dropped to a large finite value, will keep dropping eventually the gradient may become very small. Now look at a direct physical evidence here. The part of liquid, the depth of liquid which was involved in diffusion of A is here up to at 0 plus a short distance here. At a larger time, this depth is increasing, which means the liquid film thickness or liquid phase thickness which is offering resistance for diffusion, that is increasing. Okay. Now what is the intuitive understanding of this? If I have larger and larger depth of liquid offering resistance for diffusion, would it mean, what would it mean to the liquid phase resistance? If I have greater thicknesses of liquid participating in diffusion, and if I were to think of liquid phase resistance, say capital R subscript L, what would happen to that RL from here up to here? No, I am asking what would happen to RL over time, resistance offered by the liquid over time. It will increase. Flux was infinite, gradient was infinite, so resistance was 0 here, right? As greater and greater depths of liquid come into picture, more and more resistance will be offered by the liquid, and so liquid phase resistance capital R subscript L will keep on increasing. We will take one step back. Say resistance has increased to a substantial value. In that time, say about 100 seconds, whatever, resistance has increased significantly in the liquid phase. We take a step back and ask what would happen to resistance in the gas phase? No change. The resistance in the gas phase will remain same. So the total resistance, say R capital R subscript capital T, which is equal to Rg plus RL, will have Rg constant, RL increasing with time. Is that clear? Everyone? People at the back, far end? Okay. So this equation now you keep in mind, RT equal to Rg plus RL. RT on the left hand side will increase with time, RL on the right hand side will increase with time, Rg on right hand side will remain constant. This problem is about finding when that initial gas phase resistance attributable to the self collisional barrier becomes 10% of total. You see, the statement of problem is at what time does the initial resistance to access of gas become 10%, only 10% of the total. Initially it was 100%. Now in this equation RT equal to Rg plus RL, Rg will become 10% of total. This is increasing with time, this is increasing with time. This will become 10% of the total when it becomes related to RL, when the liquid phase resistance becomes 9 times the gas phase resistance. Then the total will be 10 times Rg, and Rg will become 10% of the total. Clear? So our question about finding the time at which Rg becomes 10% of total will be reduced to finding the time when RL becomes 9 times Rg. Now is that clear? Now only thing which is remaining is writing the expression for RL, the liquid phase resistance, in terms of time. You have been given this piece of information that penetration theory is the operating mechanism to describe the process of diffusion. Then according to the penetration theory, tell me what will be RL in terms of time. I hope you have not forgotten penetration theory altogether. So what is the resistance in terms of mass transfer coefficient? Say we want RL in terms of KL. Penetration theory doesn't have S. Surface renewal theory has S. Instantaneous mass transfer coefficient, according to the penetration model, will be root of dA by pi t. Average is 2 root dA by pi t. That will be the flux. Instantaneous. Function of time. This is also function of time. And it will be root of dA by pi t into C star minus 0. This is the driving force. This is the rate. Rate is driving force by resistance. So reciprocal of this will be resistance. When you take this in the denominator, that will be resistance. So in principle you can find this time t. Now is the strategy clear? First understand this. If this is clear, then calculating the numbers will be quite easy. I am not seeing the confidence even. Okay, take 30 seconds to let it sink in. Don't worry if you did not recollect the Master's question for penetration theory. It was only my way of chastising you. When you study, you will remember, nothing to forget about it. So forget, that is the ball gone now. Concentrate on now. Current is voltage by resistance. Voltage is the driving force, resistance is resistance, current is rate. NA is the rate here. Driving force instead of voltage is CS star minus 0, and the resistance will be that root of pi t by dA, right? That is RL, and that RL is 9 times RG. So if you know, if you calculate RG, 9 times that is equated to this root pi t by dA, and then you can calculate time. Nothing difficult here, is there? Now only question is, next step is, how do we calculate RG? For that you have been given flux, but that resistance will have to calculate in terms of liquid. That's why there is a term here used, equivalent resistance. So we'll have to have this RG in liquid terms. 50 meter cube per meter square per second, that gives you, you can convert into moles per area per time, the flux. If that flux is divided by CS star minus 0, and you take reciprocal of that quantity, that would be the resistance corresponding to the gas phase but in liquid phase terms. So try calculating. That is where this diagram was important. You are considering a transient situation. Time starting from 0 marching in time this way. It will be only one specific time at which this resistance is 9 times that fixed constant. So we want to know that time. Before and after that also there is a variation, right? So we are not talking of average now, we are talking of instantaneous resistance. These resistances, as I said, this is function of time increasing with time. This is going to define a particular moment at which this is 9 times this, and that is the situation we want. Penetration theory, let me give you a recap. I don't mind telling you infinite number of times. Penetration theory was the model invented by Higby to overcome the limitations of film theory. Film theory was stuck with the steady state, no dependence on time. Higby recognized that that is not the case. In reality, you don't get that much time to attain steady state. So the actual time of contact is short, and in that short time, if there is no steady state established, then you have to take the dou C by dou T term. The transience has to be taken into account. Okay, and in that he said, let there be a short time, something like theta, let's say, which will be of the order of maybe 0.025 seconds or something. So over that short time, let the diffusion be unsteady state diffusion, and you calculate the flux which is function of time. At the end of that short time, the element will go away, mix with the bulk, and as far as the larger time scales are concerned, we may need only average. But the basic solution of the diffusion equation is one of unsteady state problem. So CA is a function of Z and T, T being maximum up to theta, which is itself short, and because CA is function of T and Z, the gradient is going to be function of T and Z everywhere. At Z equals 0, it is going to be function of time. So the flux is going to be time dependent. In this problem, the central focus is to determine that time at which this transient description identifies when the liquid phase resistance becomes 10% of total or 9 times the liquid phase resistance. It is that only because we have been given that the penetration theory is able to account for the mechanism. It has been given in the problem. Okay. Since penetration theory description is given, we undertake this responsibility of dealing with the problem in the transient fashion, unsteady state. So this element itself may be short, it may go and mix with the bulk, but that's not our concern. Our concern is at what time does the liquid phase resistance become significantly large compared to gas phase resistance, 9 times the gas phase resistance. Here penetration model means overall time will be short, okay, but for us it doesn't matter now what time it is, because these times are going to be much shorter. Anything else? don't be hesitant. Ask me questions until everything is clear. If this is clear, can you calculate the initial gas phase resistance in liquid phase terms? Let me put the question that way, because that is what we will have to account for. See, the difficulty is in the gas phase there is no gradient of concentration. You get that? The concentration profile is flat. So there is no way of finding the resistance in the gas phase by its own analysis. We can have a value like this 50 meter cube per meter square per second. That value is there. But we have no means of calculating the resistance in the gas phase in gas phase terms. But we know that the flux given at time 0 could be measured as flux in the liquid phase with some equivalent thickness. And while explaining this earlier, I had replaced the gas phase altogether by a thin film of liquid here, additionally placed before the interface, which would offer the same resistance as this gas phase resistance collisional barrier would offer. So the question is now, what is that resistance in the gas phase but in liquid phase terms? So rate equal to driving force by resistance. If I were to measure this flux in terms of driving force within the liquid by equivalent thickness of liquid film, that driving force will be Ca star minus 0. If I divide this Ca star minus 0 by the flux given 50 meter cube per meter square per second, changing it to k mole per area per time, I will be able to get the resistance value, but in liquid phase terms of equivalent gas phase resistance. Yeah, this is RT. See, this is root dAB by pi t is in the liquid phase. Okay, this is the Master's coefficient. Reciprocal of this is the resistance in the liquid phase. Okay, what we are saying is, if I want the resistance in the gas phase, this equation is not valid any longer for gas phase, because I have no means of analyzing this problem. It's a flat concentration profile. But I know this value there, which is 50 meter cube per meter square per second, I convert into k mole per area per time. Okay, and I use this driving force in that additional liquid film, which gives me same resistance in the gas phase. And then the resistance, which will not be this root dAB by pi t, but whatever I am trying to evaluate, Rg in terms of L, that I can get by dividing this by that. So we cannot apply penetration theory to the gas phase. We can apply it only for the liquid phase. We want to know the time in which gas phase resistance becomes only 10% of total. I have a means of calculating liquid phase resistance, but I have no means of calculating the gas phase resistance. So I will choose to measure the gas phase resistance, which is a constant in liquid phase terms. And liquid phase terms means it is some Rg which I want to determine in liquid phase terms. So that will be obtained if this is, let's say, over here RGL, then RGL will be Ca star minus 0 by this 50, equivalent of 50. No double counting. This is the subtler point. Okay, just a minute. Now, can I rub this diagram? At least is this much clear? Let me draw two diagrams. Gas, liquid, gas, liquid. In one situation, I talk of gas phase concentration profile to be flat and concentration profile advancing in time in the liquid over time. In the other case, I take an equivalent situation. Whatever is the gas phase resistance here, let's say this is Rg. I want to measure it in terms of a liquid film offering equivalent resistance, because this is a constant. This liquid film is also a constant thickness, equivalent thickness, in which the concentration profile varies from Ca star to 0. In this, I don't talk about the time at all, except for getting this constant resistance. If resistance is constant, equivalent thickness of liquid film offering the same resistance will also be a constant. The driving force is Ca star minus 0, and let's say this Rg is expressed in terms of liquid phase resistance, which I call RGL, equivalent resistance in liquid phase terms. Okay, how will I get this RGL? That was the question. So I will use the same equation Na as, say, driving force divided by the resistance, but it will be RGL which I want to determine. The driving force is Ca star minus 0, corresponding to that thickness, and this is RGL, and this is corresponding to 50 meter cube per meter square per second. So from here I can obtain RGL. When this RL becomes 10 times of this RGL, I will know what time it is. That's it. And that time comes out to be of the order of 10 picoseconds. It means it's so short that for all practical times, gas resistance can be neglected for pure gases. That is for RL. That should be 9 times RGL. That's it. Okay, try solving this. If you don't have the answer, again we'll discuss tomorrow.